The reason we introduce vectors in physics is so that we can apply it to more complicated motions than if we had just straight line motion or one-dimensional motion. So in the diagram that I've got shown on the screen right now, let's pretend this is the surface of, let's say, a tabletop. So this is like a bird's eye view. Something on a tabletop. And let's just say that the object is in motion. If I give a little arrow here to represent that that's its velocity, we could create a list of variables for this object that's in motion on this tabletop, and we would say it's one-dimensional. We could say that that direction right there is the x direction. And in that case, we could come up with an equation of motion for the object that might look something like this. X is equal to the original x position plus v0t plus 1/2 at squared. Just a standard one-dimensional kinematics formula where we could say, oh, maybe that is position x equals 0, so wherever it started, it's got an initial position, it's got an initial velocity, and let's say, well, let's just go ahead and say that maybe that it's rolling towards the right as shown, but what if there is an acceleration going against its motion? What if it's slowing down? What if, for some completely odd and ridiculous reason, there's a stiff breeze blowing this way, and as the ball's rolling, the breeze or the wind is preventing it from going forward as fast as it would like to. It starts to slow down because the acceleration is going against the direction of motion. We would have all those quantities that we could measure, we could put into a formula. Technically speaking, it's one-dimensional motion, but it's still could be thought of as a vector problem. It's just a vector in one direction. So I would be able to take this equation we have, and I can change it into a vector equation by putting a little vector barb hat or arrow hat on top of the x there. And then each of the quantities that we measured as a vector, it's a displacement, x0 is in a particular direction, it's towards the right. And we could put that as a little vector hat on top. The original velocity isn't towards the left, it's to the right, so it's got a direction as well. And the acceleration also has a direction. So those are all their own little vectors. Now, if we knew what those quantities were, we could actually just attach positives or negatives to those values. So for the situation of this particular object, we could translate this to say that the position is going to be equal to positive xo plus vo times t minus 1/2 the magnitude of the acceleration multiplied by t squared, where a as a number is just the magnitude of the acceleration maybe, and the negative sign takes care of the direction. And all of that we could put in parentheses and put a little I hat, because the function x equals has to be a vector, because the x has the little hat over the top of it. And it's only going in the x direction, so we use the little I hat as the unit vector. But that seems kind of ridiculous, right? I mean, we're going to a lot of trouble there to kind of write that something's just going in the x direction, and we already know it's only going in the x direction, so why the big fuss? Well, what if it's not going in the x direction on its own? What if the initial velocity were, instead of pointing that direction, were pointed like so? What if the original velocity was at some angle to the x-axis, and there was still this acceleration right here? Well, that acceleration is only directed in the x-axis. It's not directed in any sort of other axis. We can actually add in a y-axis here now and say that this is two-dimensional motion. Let me fix my x-axis there. That acceleration is only going to affect the motion in the x direction, not in the y direction. Nothing's trying to speed it up or slow it down in the y direction. So if something is moving in a direction that's not lined up with the x-axis or the y-axis, like I have now, then I need to treat each dimension separately. I need to be able to separate quantities like initial velocity, acceleration, position for the two different dimensions, and that's where vectors can come into play. Now, it can get really complicated too. In this case, we could still have the position of the object in the x direction shown as such, but we would need to fix some stuff. In fact, let's go ahead and clean it up a little bit, because in one dimension, it would be that equation. Actually, let's erase the whole thing. I don't know why I left any of it up there. But now our initial velocity is not directed in the x or the y. It's directed at some angle to the x direction. There's some angle theta there. We don't know what it is, but we would say that the initial velocity is a vector that has whatever the magnitude is, call it magnitude of v, at some angle theta. And we need to figure out what those things are if we're going to go forward. But if we want to actually use that, if we want to put something about that initial velocity into a position equation and do some calculations, we're going to need to break this into components. We need to know what the initial velocity is in the x direction and how much of the velocity is going the y direction. Because if there was no acceleration from this wind right here, the ball, of course looks like a ball, would just continue rolling along that direction that the VO is pointed, and it would continue that way until something hit it or sped it up, slowed it down, fell off the tabletop, whatever it happens to be. It would just keep going that direction. So we could just call that the x direction. We can rotate our coordinate system. We don't have to have it, up, down, left, right on our paper. But because there's an acceleration, that means in the x-axis direction, we're going to have some change in velocity. It's going to slow down in that direction. So what might the path of this ball look like if there's a stiff breeze blowing on it from the right? Well, as it goes along its original direction of motion, the wind pushing it is going to try to make it go to the left. So it's probably going to follow some sort of an arc, like this. That's probably the path it'll follow. In the y direction, the kind of up and down on the page that we have, it's not going to change. It's going to keep going the same speed because nothing's speeding up or slowing down in that direction. There's no acceleration on our y-axis. So in order to be able to calculate what this ball is doing, what now seems to be kind of complicated motion, we need to split the original velocity into components. Now, in a previous video, I showed that you can get the magnitude of a vector using distance formula sort of calculation. But in order to find the components, we're going to have to set up a little trigonometry as well. So if I've got an original velocity VO, little vector hat on top, and it's making an angle theta with the x-axis, I can say that that's the hypotenuse of a triangle. The VO is at an angle to an axis. Well, let's just go ahead and make it the hypotenuse of a triangle because we know how to do math with triangles, especially with hypotenuses or hypotenusae. I don't know how you say that. So this horizontal leg of the triangle is the x component of our velocity. So we can call that VOX. And it's a vector. We could put a little vector hat on top of it. It would be going in the I direction technically. And then the vertical leg right here is going in the y direction, and that's going to be VOY. That's a vector. And we can just follow basic trigonometry to figure out what these are. So VOY is going to be VO multiplied by the sine of the angle theta, and VOX is going to be VO times the cosine of the angle theta. We can calculate what those are, and we could use those for number crunching or whatever needed to do. But what's most important is we can write out equations of motion, the kinematics equations for the motion of this ball, in both dimensions. We can write a y equation and an x equation. And we can do that all in one gigantic equation, or we can split it into two parts. So let's make that happen. In the x direction, put x colon here just to kind of start us off there. That's not a sideways emoji for somebody ready to barf or anything. So in the x direction, we could say that we've got the function x is equal to x naught plus box t plus 1/2 a t squared. And the y direction, you could say y is equal to y naught plus boy t. And that's that, because there's no acceleration in the y direction. There's only acceleration in the x direction here. Again, we're talking about something on the top of a table rolling. It's not, this is not like a side view of a ball being thrown in the air. We'll do those later. So the motion could be shown using this formula. And if we wanted to kind of condense all this down, we can say that the position of the object, not in the x or in the y direction, but in any old direction that it wants to be pointed at, we're going to give that the vector r. R is going to represent any sort of two-dimensional position in a coordinate system. So if I'm at the origin and I move to a position up here, then the r vector would just be drawn. It's got some x and it's got some y component, but it's r. So we can think of that in terms of a radius from a center pointing out. It doesn't have any specific direction. It's always just pointing away from the origin. So we can say that r is equal to x plus y. Those two vectors combined together will give us our r. So it means we can also write it as the x vector's magnitude, or whatever is making up that vector in the I direction, plus the y vector, I keep wanting to put a hat on top of that, in the j direction. Not exactly the most streamlined way of doing things, but let's go ahead and set up what this would look like if we actually had some numbers for these things. And what we're also going to do is just, let's say it's at the origin, because that would just make life a lot easier, right? So let's go ahead and set that up. So let's say that that initial velocity is, well, let's just make it a nice number for us here. Let's go ahead and say that it's 10. So it's 10 meters per second at an angle of 45 degrees. So we only have to calculate something once when we come to components. And let's say that our original position is going to be 0. Let's say that we're declaring this as the origin. So our xo and our yo are both going to be 0. And let's go ahead and give a number for the acceleration rate as well. Let's say that the acceleration is going to be, let's say 2 meters per second. And it's going to be in the negative I direction. So it's pointing in the negative x direction. Now, if we wanted to kind of condense down all of these things into the formula for position, we can go ahead and write it for the x direction and the y direction. So the next step is going to be to calculate the components of this VO, because we need to know what the components are to put it into the equations. So for the x direction, we go and calculate that out. Vox is going to be the 10 meters per second multiplied by cosine of 45 degrees, and that's going to be in the I direction, which should be, oh geez, what is that, like 707 or something like that? 7.1, maybe let's call it that. Cosine 45, yeah, let's call it 7.1 meters per second. And that is in the positive I direction. And then VOY is just going to be the same thing, because we chose 45 degrees to make our life easy. It's going to be in the J direction. Once we got that, we got some values we can put into here. We already know what the acceleration is. We wrote it down over there. So we can write this, these two equations out, and then we can combine them. After we do a little simplification, we'll combine them and put them into the R equation. So for x, up here, we'll have 0 plus 7.1t plus 1/2 negative 2t squared. And all of those are going to be in the I direction. So it is everything that we have for the x function right there. And then for the y function, it's going to be 0 plus 7.1t, and then nothing. We're done there. And that'll be all in the j direction. So if we want to condense these things into our r vector, we could write it as the r vector is equal to 7.1t minus t squared, I direction, because the 1/2 and the negative 2 simplify, and then plus 7.1t in the j direction. And then all of that, we can eventually put brackets around it and say is measured in meters. Not the easiest thing to kind of set up. All right, that's a lot of work there. But what we can do is, well, there's a lot of stuff we can actually do with this. This is kind of cool. So we're going to take a look at how we can take derivatives of this to find the velocity at any given time, including its direction, the acceleration as well. So we'll pause here because we're already going on a little bit. So second video for this, we'll go through how we can manipulate this function in order to get more information.